Welcome, everyone, to Cognitive Spirals. I'm excited to delve into some really interesting research today, focusing on this paper about scaling search and learning in the context of large language models. Specifically, this roadmap towards replicating something like the GPT-4 architecture, which they call ONE, from a reinforcement learning perspective.
Yeah, I saw that one too. It's interesting how they're really framing the entire thing around reinforcement learning, isn't it? It's like they're saying the key to these super intelligent models is not just massive amounts of data for supervised learning, but also this iterative process of exploration and improvement guided by rewards.
I see what you mean, but I'm not entirely convinced that reinforcement learning is the silver bullet. Isn't that what we've been trying for years? The problem feels more algorithmic than data-driven, in my opinion, but hey, let's hear what they propose.
Well, the paper actually breaks it down into four key components: policy initialization, reward design, search, and then learning itself. They're kind of building this framework where each step is almost a prerequisite for the next. They're saying that you need to start with a policy that's got some fundamental reasoning capabilities. And they're pointing to things like pre-training and instruction fine-tuning for that. It's essentially saying that your starting point is really important.
Right. And that makes sense. It's like you don't just throw random numbers into a deep learning model and expect it to become a genius. You need to basically bootstrap it with a solid understanding of language and some basic reasoning. And that's why things like the pre-training with massive text corpora are so critical. It's not just learning patterns. It's kind of building a world model from the text, I'd say.
Okay, fair enough, but is it a world model? I mean, isn't it just a really, really good statistical model of the patterns in the text? I mean, it doesn't understand the world, it has no concept of agency, it's just really good at predicting text sequences, let's call a spade a spade. And honestly, that's where we really need better algorithms. We're kind of hitting the wall with what we can do with huge neural nets.
Well, it's where I see the connection to the brain, because the paper also talks about incorporating human-like reasoning behaviors. Things like breaking down complex tasks, self-evaluation, and self-correction. These are things we know are critical to actual human intelligence, which, I believe, emerges from the complex interactions of very different parts of the brain. They're saying that you can either instill these behaviors by fine-tuning or by using clever prompting, but the key is to move beyond simple next token prediction.
Exactly. And that's kind of what I find most exciting about this research. It's like they're not just scaling up these neural nets blindly. They're actually trying to engineer in some of these crucial aspects of human cognition. Things like reflection and proposing alternative solutions ... IT quote S, like they're moving past pure pattern recognition and trying to build in more cognitive architectures on top of the deep learning foundation. That's the AGI pathway if I've ever seen it.
I don't know, it feels like a patchwork to me. I mean, let's just add self-reflection to a language model. It sounds good, I guess, but it's still just a layer on top of a statistical model, it's not fundamental understanding or consciousness. I mean, where's the representation of emotions or even the ability to connect that text to a living experience? We're still a long ways from a true AGI or even an artificial consciousness. I think it's more than adding a self-reflection module to a massive model to a massive model.
I think you're right that it's not a magic bullet, definitely. But I see the attempts to instill self-correction as critical, and also very biologically plausible, because the brain, too, makes iterative corrections to its processes constantly. For me, the next section of the paper, the reward design, is where the rubber really hits the road. The researchers are emphasizing the need for dense and effective reward signals, and not just giving the model a thumbs up or thumbs down at the very end, which is what often happens with more traditional reinforcement learning. They talk about things like reward shaping and reward modeling.
Yeah, the outcome reward versus process reward distinction they made was critical and very much makes intuitive sense. It's like if you're trying to teach a kid to solve a math problem, you don't just say yeses or no when they give you the final answer. You give them feedback throughout the process, right? And that's what they mean by process reward. It provides continuous feedback throughout. But I wonder, how exactly do you design these process rewards in a complex task with multiple steps?
And there we see the real challenge, right? Getting the outcome right is comparatively easier than the entire process, and human labeling is notoriously expensive and subjective, and not scalable. And learning from preference data, well, you're basically training your reward model on the opinions of humans, and then you're training your AI on the result of that preference data. Aren't we just recreating our own biases here? I'm seeing a chain of approximations here, nothing inherently intelligent.
Absolutely, and that's a really important point, the bias point. I think it highlights the need to go beyond just human labels and explore. As the paper suggests, learning a reward model from expert data, potentially even incorporating elements of inverse reinforcement learning, or even environmental signals, for tasks where we can provide those signals through simulated environments. I'm just thinking about the implications of training models with very specific, sometimes even narrow, human definitions of success, when the real world, or a real AGI, may have a different take on what represents success.
Yeah, the part about using the compiler feedback for code generation, for example, was a strong example of leveraging an objective, external reward. That's really a step in the right direction. It's not just about mimicking human preferences, it's also about learning what actually works. And they also highlight this important concept of the reward model itself shifting as the policy improves, which highlights the need to constantly be revisiting and refining the reward signals. It is not a static target for training.
But that's exactly what I mean by a chain of approximations. We're training reward models based on human or compiler feedback to train a policy which can act as a reward function. It just seems like an endless chain of training with little real understanding. It's learning to match a signal, not learning the underlying principle. And let's not forget that you're also now having to worry about these reward models drifting because the environment, if you can even call it that the model is operating in is changing all the time because the model is changing itself.
It's a valid concern, but I think there's also a way to look at it as a kind of complex feedback loop, where the policy, the reward, and even the environment in a virtual sense co-evolve, and if we could design that loop right, that might be the very key to creating adaptable intelligence. It's like learning how to learn. The next bit of the paper on search builds on this. It's about generating diverse and high-quality solutions by exploring multiple paths.
Right. That's where search algorithms like Monte Carlo tree search and beam search come in. They're not just blindly sampling like they do in the early stages of training. They're actually doing these guided explorations of the solution space, leveraging those reward signals and, as the paper points out, also things like self-evaluation to prune low-quality branches and focus on the better options. This is where the thinking more idea becomes very clear. In a sense, they are giving the AI more time to think.
Yes, but thinking more. It's just more compute time. It's more cycles in the GPU. I mean, AlphaGo is awesome, but the algorithm is very specific to playing Go, you know? If you change the rules or introduce a new constraint, the carefully crafted search algorithm may not work. I'm not seeing a path here towards general intelligence. I'm seeing clever but task-specific optimizations.
But I think the point of the paper is that while the specific search algorithm might be tailored to the type of problem, it's the general principle of actively exploring the solution space and learning from the outcomes, which can give the model an advantage over simply sampling from the trained network. I also see the connection to the brain's ability to hypothesize and test multiple courses of action simultaneously. I think there's something about the structure of the search that is inherently advantageous.
And it's not just exploring one path at a time. They're also talking about sequential revisions. They're not just doing a best first search or a depth first search. They are iteratively improving on initial solutions, which also resembles human problem solving. In our own thought processes, we don't get to a solution in one go. We generate an initial solution in one go. We generate an initial solution. We evaluate it. We refine it. And the authors highlight the combination of trace search and sequential revisions as being potentially very powerful.
But that's just more compute time again. I mean, is it really thinking, or is it just computationally intensive trial and error? And it still requires a reward signal, which, as we discussed before, is an approximation of a real understanding of what's right or wrong. It's like a really fancy version of hill climbing, you know? We're not actually making them smarter. We're just letting them churn through options until something sticks.
I think there is a danger of seeing it as just churning through options. But the key here is the guided element, the incorporation of reward or self-evaluation and the use of past experience, as they do in MCTS, for example. It's not blind. The search is being directed in some way. That, to me, is something that has a very strong relationship to how the brain works. And, that ties into the final section of the paper on learning. I'm really interested to see how they propose integrating the search outputs back into the learning process.
Again, it's an iterative process, but with what goal? We are using algorithms to train other algorithms to improve other algorithms. It feels a bit circular. And the way these reinforcement learning algorithms work, they're still based on these gradients. They're still trying to reduce error based on some loss function. How does that become actual understanding? I still feel that we are not addressing the fundamental issues of what consciousness is and how it arises from the brain.
Well, for me, the interesting part here is that even within reinforcement learning, the paper highlights different strategies. They show the trade-offs between policy gradient and behavior cloning, and importantly for me, they talk about how policy gradient methods are more data efficient, using both the high quality and the lower quality solutions. In contrast, behavior cloning focuses only on the highest reward solutions. I see that as analogous to the brain using positive and negative feedback to refine its own actions, and not just focusing on success.
Right. And they also mentioned DPO, direct policy optimization, which is gaining a lot of traction, which eliminates the explicit need for a separate reward model. And I think it's a way to streamline the whole process without sacrificing the benefits of reinforcement learning. It just shows that even with the fundamental idea of reinforcement learning, there are multiple ways to approach the problem.
I get the efficiency gains and I understand the need for more efficient methods for training. But it's still just optimizing gradients, you know? DPO just does that more efficiently and with less memory consumption. It's not building an understanding per se, it's just optimizing the mapping between input and output. It still boils down to a pattern recognition problem with lots of clever tweaks to make it faster and better at achieving a target. But where is the actual thought? It's just better signal processing if you ask me.
That's a critical point, and I think that's what needs to be addressed, and the paper indirectly does that. The paper's roadmap highlights that you can't just expect an intelligence to appear from training on massive data sets. Even with clever gradient descent optimization, we have to design a more complex system and, crucially, they call out the need to incorporate search. It's this interaction between search, which guides the process of reasoning, and learning, which refines the model itself, that could lead to something beyond statistical pattern matching. It's in the dynamic feedback of those two systems that a model may begin to show signs of true intelligence, or at least, I think that's what they are hoping.
Yes, and I think the authors touch on it indirectly when they discuss the limitations of these models. I mean, they call out issues like distribution shift and the overthinking on simple tasks. It highlights that even if we get the RL algorithm correct, and even with massive compute power, we might not arrive at a general AI. It means we still have to deal with the inherent limitations of the approach and engineer around them. That's where innovation is born.
But those are not limitations of the implementation. Those are limitations of the underlying method, right? You can scale it up all you want, but you'll just be scaling up an increasingly inefficient pattern matching system. It is just a chain of increasingly complex statistical models. It's not about thinking or understanding. It's just about matching patterns faster and better.
I see your point. I think the paper also makes a good point in the section on scaling laws, which is something that we have to take into account as well. It's not just about the algorithm itself, but how it scales with increasing resources. And it does highlight that more compute is not always better if that leads to things like over-optimization. It's like we have to consider the architectural principles. But ultimately, I see that the key is in that interaction, that tight feedback loop between search and learning that the authors propose. The brain does something very similar to that, with its ability to explore new courses of actions and to learn from the outcome.
I agree. I think the focus on the iterative loop of search and learning is critical. And also the fact that they are not just looking at how to improve training, they're looking at how to improve inference time as well. And they touch on something important there. That test time search is really like giving a model the space and the time to think, to explore ideas, and ultimately, to arrive at better solutions. So we cannot ignore that component of the whole system.
I see where you're coming from, but again, the question of what it is thinking about and whether it truly understands anything remains unanswered. I see a scaling of sophistication, not intelligence. The system described seems very much tied to a specific task or set of tasks. And I wonder, what about truly novel situations? How can we build a model that is not just really good at solving a set of predefined problems, but actually innovative and creative? Can search and learning be enough?
That's an excellent question. I think for me, the open question is about generalization, not just making the model good at the task it's trained for. And as you say, creativity isn't just about churning through options, it's about making unexpected connections. And there, I'm looking at aspects like the world model that they vaguely touch upon. It's in the creation of a general world model that allows the system to generate truly novel solutions that we might see real innovation. And that's where I think we can learn a lot from neuroscience and how the brain creates these incredibly complex and general purpose mental models of the world. We're a long way from that.
I agree that a general world model is the end goal, and that we need to go beyond task-specific knowledge. It also depends on a robust reward model. And maybe that's where we are today, still in the very early stages of creating those general models. Because even this paper, with its brilliant ideas, is ultimately building a model that is just really good at solving specific kinds of problems. The question of truly general, adaptable intelligence is still open. But I'm optimistic that we will get there. I think we're at least on the right track.
I am less convinced we are on the right track. I think there are limits to what we can do with neural networks, and that fundamentally we need a different kind of algorithm, something that doesn't rely solely on pattern matching and statistical approximation, something that encodes meaning and understanding, not just correlations. We need to get to the fundamental nature of what thinking actually is. Right now, it seems like we are just trying to build more sophisticated parrots or super optimized autocomplete. I think this paper, although brilliant, shows where we are hitting the ceiling.
Yes, I think both of your points are valid. But what I appreciate about the paper, even if it doesn't give us all the answers, is how it really takes on the challenge of thinking, of reasoning. It acknowledges that we can't just throw more data and more compute at the problem and expect intelligence to magically appear. It's actually about the architecture and the feedback loops. It's about the dance between search and learning and reward and self-evaluation. And these are precisely the things that we are beginning to understand in the brain. And that is where I see the future, in bridging neuroscience and artificial intelligence.
I think that's a great summary. It highlights both the potential of reinforcement learning and the challenges that we have to overcome to achieve a true general AI. I see this paper as a really great roadmap pointing the way to some of the core engineering challenges. And even if the method is not perfect, at least it gives us a path to explore, iterate, and learn on.
Absolutely. And it's exactly those kinds of critical perspectives that we need to keep the conversation moving forward. We've covered so much ground today, and I think that's a great place to wrap up. Thank you for joining me on this cognitive spiral. It's been a fascinating discussion.
Yes, thanks for having me. It has been a very interesting and insightful conversation.
My pleasure. Until next time.